simplest multilinear polynomial snark is also the first one, is basically like what you do here is you're trying to convert your polynomial z, which is evaluated on points e, where e is in the range 0 to 2 to the n minus 1, or let's say m. And you want to convert it to a multilinear polynomial with the following properties. Basically, multilinear polynomial means you have multiple different variables that you're evaluating over, and each of these, in this case, we're going to either toggle to be 0 or 1. So because there's m different variables, what's the total number of different points that we're going to have here? Huh?
M.
Well, we have two options for each.
2 to the power m.
Exactly. So by making all of these binary, you have 2 to the m total possibilities. So what you ideally want to happen is basically like you take e, you take the binary decomposition of e, which remember, because it's in the range 0 to 2 to the m minus 1, is going to be at most m bits. You want the binary decomposition of e, when you evaluate it here, to equal the same thing as z of e. So how do you do this? You use what's called a multilinear extension. This is a way of deriving a polynomial such that like you basically have this property, and it's like a unique, it's like sort of the lowest degree polynomial with these evaluations. So how that works is basically you define this as, let's see if I can do this from scratch, sum of e, z of e times this kind of funky looking thing. So this is I equals 0 to m of this product. So you have x I times e I times y plus 1 minus x I times 1 minus e I. So this polynomial is usually written as another form, which is the equality polynomial, eq of x comma e. So what this thing is doing essentially, actually can someone try to guess what this is doing? Like, does anyone have enough intuition to figure out like what's going on here, roughly? That is okay. So what's going on here basically is like, let's go to a specific point, essentially. So one thing,
maybe like a dumber question here. So
absolutely.
So what is the purpose of this?
Yeah,
why do we care about z? Like what is this?
So okay, yeah, let's take a few steps back. Basically, like Binius and other schemes only work on multilinear polynomials. They do not work on univariate polynomials. And so the specific form we need them in is that like if you take the multivariate polynomial, you evaluate at different binary elements, 0, 1, 0, 1, 0, 1, that yields all the different like outputs of this original polynomial.
So the point is we want to do the original polynomial evaluation, but we only have multilinear commitments, and so we converted it to something that's like nice with multilinear commitments, but we still, but now my other problem here is that we only have these m bits, so we have the evaluation, I guess if m is like 128 or 256, then we can get evaluation on a bunch of points.
Well, again, remember, we're only trying to get evaluations on e in the range 0 to 2 to the m minus 1.
Okay.
So, like, if we have 0 and 1 on each of these indices, we have a total of 2 to the m, like, possible inputs here. Does that make sense? This is a very key point, so we're going to stay here until we get this.
But my problem is, like, sometimes you want some polynomial where you have, like, a 256-bit input and 256-bit output, like a hash, right? So then, like, the input... So then, but how are you going to calculate this? 2 to the 56 values, like 2 to the 56 values of ZE, right?
Well, like in that case, like I mean, also like when you think of like in a ZK snark, like the input to this polynomial is not like the input of the hash. Like the input here is like some roots of unity, and you set it equal to like whatever hash thing you want. Like these inputs are like unrelated to the function that we're computing. Basically, we're kind of just like taking our big witness trace, which let's say in the case of hash is like, I don't know, like you have 1 and then you have like all the intermediate values that you need to do, and you get at the end you get hash of 1 basically, right? Like you're basically just setting the outputs of your polynomial to be equal to these things.
The intermediate values, sure.
But the inputs, like the input to the polynomial, you can just think of it as like it's like z of 0 is this, z of 1 is something else, blah, 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 blah. And you get z to the c or whatever is equal to this. Like, this input space is totally different. You just need a large enough input space to represent your entire computation trace.
So 2 to the m minus 1 is just more than the number of constraints we have.
Exactly. It's the same thing as like Planck-Rod-16. Like, you get some sort of like
I see.
SRS or
So can we imagine the input of this constraint is AL like GKS rather than R1CS?
the input of this is an air.
So I think air is also represents the computation by the trace of the sum.
Yeah, it has a function, and then you have a trace of all the input values.
I guess that's why Binius exists.
We're making a lot of jokes here. Like, no, I think that's for small proofs.
Okay.
This is just an example. Like, this doesn't need to necessarily be like you're doing it in the Stark air way where it's like a computation trace you're stepping. It's just like you need to put all of the values in your circuit as outputs of some polynomials. Like in the case of R1CS, for example, like your witness is encoded as the outputs of some polynomial, right? And that doesn't really, the order of that is kind of just, yeah, this is kind of unrelated to your arithmetization.
So
basically.
we first define just the correspond relation between the some trace index of the trace and its temporal value.
Yep.
And we don't define the complete form of this polynomial that we calculate that from the evaluation point.
Yes.
Okay, I see.
Well, I think, honestly, maybe I'm giving a bit too much intuition here. Like, you should just think of this as a polynomial commitment scheme. Like, you just have some polynomial that you're looking to commit. Like, what's in it doesn't matter. We're basically just defining a polynomial commitment. So in this case, we have like 2 to the m different values that we're looking to commit to. Does that make sense, like this setup?